Welcome back to the classroom. My name is Mr. Wong, and in today's lesson we're going to be looking at the activity series of, it says elements, but we are looking at metals. So we're going to look at the trends on the periodic table, and we're going to look at, in terms of metal activity, how can the metals activity relate with ionization energy, atomic radius, and electronegativity. So in the previous lesson, we were talking about how metals react in water, with oxygen, and with acid. So what dictates how reactive a metal is? What are some properties of the periodic table that can tell us that information? So if we're looking at the activities of metals, generally speaking, as we go down the group, so down the column, so lithium, sodium, potassium, rubidium, and cesium, it actually gets more reactive. We know there's a general trend. We know that alkali metals, or group 1 metals, are the most reactive type of metals on the periodic table. We also know halogens are the most reactive nonmetals, but that's not part of what we're looking at today. We're looking at why these metals are the most reactive and why the reactivity rate gets lower as you go across the periodic table here. That's what we want to investigate. So we're going to start by looking at a thing called atomic radius. So atomic radius is the distance between the atom's nucleus and the most outer electron. So if I wanted to illustrate that, I would have the nucleus in the center, and then I'd have my most outer electron. Obviously, this is the simplistic interpretation of what the atom looks like. The atomic radii is that distance there. What we can see is, as we go down the table, the radius, or radii, would increase. As we go across the table, we can see that the atomic radii decreases. So obviously the question we want to ask here is, why is it bigger and why does it get smaller depending on which reference point we're looking at? Well, the key point is, where are the valence electrons? They kind of dictate the size of the atomic radius. If we're going further across the periodic table, we increase the number of electrons and we increase the number of protons. Now one is negative, one is positive. So that actually increases the what we call electrostatic attraction between the outer parts of the atom and the inner parts of the nucleus. And that's the reason why the atomic radii gets smaller. Obviously, that can sort of explain how we go across, why that gets larger, but then why does it get bigger as we go further down? Well, you need to understand, with each row, or each row we go down by, okay, we're actually increasing the number of valence shells. So by having it here, we increase the number of valence shells of electrons. Another thing we want to look at here is, imagine if I have another valence electron shell here that's added on as I go down the periodic table. Well, electrons are both negative charges, so when we have two negative charges, they're going to try and repel against each other. So if they're repelling, this electron, instead of being in this position, might get pushed to a position further out because of that repulsive force. So that could be what's happening. If we're looking at the general trend, we can actually look at which are the most reactive metals and their atomic radius. So we talked about it last lesson. Potassium and sodium are one of the most reactive metals, are part of the group of most reactive metals, and you can actually see in correlation, for that particular part, they also had the largest atomic radius. For metals such as calcium and magnesium, which are in group 2, we can see there's a drastic drop-off in the atomic radius. and so forth with the more non-reactive metals like tin and mercury. They have a relatively smaller atomic radius, even when we compare that to lithium. So, what is reactivity? Well, reactivity is the ease of which an atom will lose its valence electron, or so to speak, how likely is the outer shell electron going to be displaced by the element. Now, cesium, which is in group 1, has the greatest reactivity, and that means it also has the greatest percentage rate of losing its valence electron. So in terms of reactivity, it goes from right to left and top to bottom. Now remember, reactivity doesn't have the same meaning as being reactive. Reactivity just means how easily is an electron lost. So don't get that confused. And if we're talking about the highest reactivity in terms of metals, it's group 1 we're talking about, okay? Group 1 metals. Okay, next one we can talk about is ionization energy. Now, ionization is the process in which a neutral atom, okay, so what we have here, a neutral atom displaces its valence electron and becomes a charged atom, or what we call an ion. In this case, we have potassium. It will displace its electron and become a positive ion, potassium ion, and it is positive plus. What we're measuring in ionization energy, or first ionization energy, is how much energy is required to displace this electron. The lower the first ionization energy is, the easier it is, obviously, to lose that electron. So again, let's have a look at the diagram that we have here. The most reactive metals that we have, we'll use this diagram here, potassium and lithium. All right, they're both group 1 metals. We can see they both have the lowest first ionization energy relative to the other metals in the row that they're in. So if the energy required to remove the first valence electron is low, then obviously it must mean that the reactivity of the metal is very high. And we know as a general trend, the ionization energy will decrease as we go from right to left and from top to bottom. That's matching the trend that we talked about with metal reactivity. The next one we want to talk about is the electronegativity of an atom. Now, electronegativity is the capacity in which an atom wants to take an electron away from another atom or another ion. That's essentially how ionic bonds are formed. It's where the cation, in this case the fluorine, is taking away the other valence electron of our cation sodium. Sorry, I meant to say anion for fluorine. As a general trend, we can actually see that the group 1 metals have a very low electronegativity rate, right? So group 1 has the lowest, and if we actually look at the halogens, which is group 7, they have the highest. As we go across the periodic table, we already said that as we go across, the reactivity of the metals decrease. We can actually also see that it's increasing in electronegativity. So instead of giving away electrons, they want to hold on to their electrons, so to speak. So electronegativity is the atom's ability to gain a valence electron. A large difference in electronegativity of two atoms leads to the formation of an ionic bond. If we actually have a look, sodium and oxygen, that is a very big difference in electronegativity, and so that's why they form ionic bonds. If we have nitrogen and oxygen, when they combine, because their electronegativity is very small, we form covalent bonds. So that's the difference there. So as a general trend, we can actually see electronegativity increases as we go from left to right, and when we go from bottom to the top. So this is the reverse pattern of reactivity. And so that's why metals decrease in reactivity as we go across, because the electronegativity, the atom's ability to hold on to the electrons, the valence electrons that is stronger. So that's the connection between reactivity, electronegativity, and ionization energy. Okay, so let's have a go at this multiple choice question. So I have X and Y formed as a compound. What type of compound will I expect it to form as, and what would be the formula? So it's in group 2, X. So we'll have a charge of 2 plus. Y is in group 7, it has a charge of 1 minus. We already talked about there is a big variation in electronegativity. Also group 2 is a metal, group 7 is a non-metal. So when they combine, it's going to be ionic. And based on the formula that we know, they will crisscross over, so it'll become XY2. The next thing we can talk about is if element X and Y are on the same period of the periodic table, what can we expect? Will it be radius size, higher electronegativity, higher first ionization energy, or higher melting point? Now obviously we haven't talked about melting point, so that's not part of the reasoning. Where Y is, it will have a higher first ionization energy than X, meaning by it takes a lot more energy to remove a valence electron from where Y is in comparison to X. Okay, so we're down and gone through all that content there. A general summary is metals that are closer to the left-hand side and further down the periodic table will be more reactive than other metals. And that's because they have a low electronegativity, which means the positive nucleus cannot hold the valence electrons in as tightly. This leads to an increase in the atomic radius for low negative electronegative elements. But don't forget, we also said it has to do with a little bit of the repulsion between the valence electrons and the inner shell electrons. We also said that because of the larger atomic radius, that leads to a lower first ionization energy, meaning that it's easier to lose a valence electron. And all these points lead to a more reactive or high reactivity metal. Okay, thank you so much for joining this lesson here. Hopefully you got a good understanding out of the different trends of the periodic table and why certain metals are more reactive than others. If you found this video useful,